Hello, let's go ahead and continue with the next section, 3.2, graphing rational functions. So to begin, let's recall some themes that we learned in section 3.1. So from 3.1, we talked about the domain, and that means what x values work. And for that, we set the denominator equal to 0. We also learned about the vertical asymptotes. So vertical asymptotes. And to find that, we need to find when it's equal to 0, again, our denominator. So maybe I should change x to denominator. And to clarify, in the domain, we set the denominator equal to 0, but we're looking for when it's not equal to 0, right? So I need to emphasize that. Something else we learned in section 3.1 is we talked about the horizontal asymptotes. And our book talked about 3 cases, but really there's 4 we need to consider. For the first case, if my denominator is bigger, say I have x and x squared, we have denominator of y equals 0. And for this, we're talking about the degree. We also have if they're of equal degree. For example, this would be made up of the fraction that makes their leading coefficients. So 3 over 2. And the third one our text talked about is if I have a numerator that's degree 1 more than the denominator, then we have a slant asymptote. And if that's the case, then I need to divide, and whatever I'm left with, disregarding the remainder, is my equation. And the fourth case that our text didn't mention is if the numerator is of larger degree, then we have no horizontal asymptote. All right, so we're going to talk about graphing strategies for rational functions, rational graphs with holes, and rational graphs across the end behavior asymptote. The topics of vertical and end behavior asymptotes from 3.1 will now become the beginning of the process for drawing graphs of rational functions. The following list below is a quick summary of the topics from the last section. So a rational function has a numerator and denominator that's factorable. Write the function in factor form. If the function has a common factor, both the numerator and the denominator, write a third version of the function that is simplified. So make sure you take off what's been canceled out. Determine the vertical asymptotes and the location of the holes in the graph by saying the denominator equal to 0. And holes, again, that's canceled off from when you factored, if it was possible. Determine the end behavior functions. So this is your horizontal asymptotes. You have the case of the numerator being less than the degree of the denominator, then you'll have y equals 0. So horizontal line at x. So our horizontal asymptote will be the x-axis. 2, if the degree of the numerator and denominator are the same, the rational function will have the end behavior of the horizontal asymptote, a equals b, where a and b are the leading coefficients of the numerator and denominator. 3, the degree of the numerator is 1 greater than the degree of the denominator. The rational function will have end behavior approaching a slant asymptote. And we use long division or synthetic to find our answer. In this point in the process, we have dashed lines that are not part of the actual graph. but will control some of the behavior of the rational function. After asymptotes have been drawn, we will now set out to find important points for each graph. As with polynomial functions, we will find and plot the intercepts. So remember, to find the y-intercept, you let x be 0. To find the x-intercept, you let y be 0, or f of x. Third bullet point, if the graph has an end behavior asymptote that is not the x-axis, just check to see if the graph will touch the asymptote. It may touch or cross it. And fourth, recall the vertical asymptotes. Divide the graph into pieces and the graph of each piece of the rational function, finding points if necessary. So let's draw this first function. F of x equals x plus 1 over x squared minus 4. If ever factorable, make sure you factor. So here with your denominator, x squared minus 4 is factorable. All right, even though it was factorable, nothing canceled out, right? Nothing divided to make 1. But we keep note that that is our vertical asymptote. By saying the denominator equal to 0, you get x plus 2 equal to 0, and x minus 2 equal to 0. You get x is equal to negative 2, and x is equal to 2. Because the degree of the numerator is less than the degree of the denominator, the function will have an end behavior asymptote, also known as a horizontal asymptote, as y equals 0, or the x-axis. So far we've drawn our asymptotes. If you look closely, we have a horizontal asymptote at y equals 0, and we have our two vertical asymptotes. One at x equals negative 2, vertical asymptote, and another vertical asymptote at x equals 2. And I like to label everything just in case we need to start from the beginning, we know what everything is. All right, now let's begin by finding our intercepts. To find the y-intercept, let x be 0. So we're left with, those were our x's, and we made those zeros. So we're left with 1 over negative 4, which is negative 1/4. So this is the point 0, comma, negative 4. Now we have an x-intercept. So for that, we set our equation equal to 0. All right, we multiply the denominator to both sides so that we can move it from the denominator's place. And what happens is when it gets multiplied by 0, it's 0. So in other words, your x-intercept, set your numerator equal to 0. That will yield the same result. Because since you're always saying your equation equal to 0, your equation is being set equal 0. To get rid of the denominator, you multiply it to both sides, causing it to equal 0 and go away. All right, our numerator is x plus 1. We subtract 1 to both sides. We're left with x equals negative 1 as our x-intercept. So now we have the point negative 1 comma 0. So let's plot what we have. We have our x-intercept at negative 1 comma 0, and we have our y-intercept at 0 comma negative 1/4. All right, now we're left to graph our function. Now remember, your vertical asymptotes, these split your graph into pieces. These two vertical asymptotes have created 3 parts we need to consider. We need to consider this part to the left of the vertical asymptote. We need to consider what's going on in the middle of the asymptotes. And we need to figure out what's going on to the right of the asymptotes. Reason being is because these asymptotes will make it so I can't cross it, right? So I'll have to go up or maybe go down this way. We don't know. We have these lines we can't cross, so we have to be careful. And because we can't cross them, this isn't allowed, it's creating three different graphs. I don't know what we're going to see. I don't know. That's the next part we're going to figure out. I just want to emphasize that we have three different parts to consider. Before moving forward, note that when looking for x-intercepts, we can set the rational function equal to 0. After clearing the denominator, however, the result always gives an equation where the numerator is set equal to 0, just as we said earlier. Therefore, to save time, we simply set the numerator equal to 0 to find the x-intercepts. Cool. Since the end behavior asymptote is the x-axis, and we have already found the x-intercept, we have already checked the graph touches. We have already checked if the graph touches the end behavior asymptote. Having two vertical asymptotes will graph three pieces. We now draw each section of the graph one piece at a time. Working from left, the first piece of the function's graph must have a left end approaching the end behavior asymptote and the x-axis. The right end is approaching and the vertical asymptote at x equals -2, it must be pointed almost straight up or straight down. Because only x-intercept was found to be -1, this piece of the graph is not allowed to cross the x-axis, and therefore must be entirely above or below the x-axis. If we need to evaluate the function at any x value left of -2, let's use -3. We only need to determine the sign of the value of the function. So what's all that wording? Well, let's take a look at this piece. We have a vertical asymptote at -2. I have two options. Let's highlight what's being forced upon by the asymptotes. So we have these asymptotes, and these asymptotes are telling us we can't cross these values. All right, I can't cross them. So if I have this -2, then I only need to know another point to test what's going on. Say -3. If it's positive, it's going to be above my x-axis, above my horizontal asymptote. If it's negative, it's going to be below. But regardless of it, I just need to know the sign, because if it's above, let's say this point is somewhere over here, then this point is part of a line that will not cross my horizontal asymptote and will not cross my vertical asymptote. So it would be forced to be a figure like that. Or if we get a negative answer, say it's a point below my x-axis, same idea. It would be forced to get closer and closer to my horizontal asymptote but never cross. Or it can be forced to get closer and closer and closer to my vertical asymptote and not cross. So we have these options. We have option 1 and we have option 2. They all depend on the sign, whether it's negative or it's positive. So let's see what happened. Again, our goal is to test a point that's left of our vertical asymptote, so let's try -3. All right, so we're trying -3. We see that our answer will result in a negative. A negative number, we know the first piece of the graph must be below the x-axis as follows. So I have some negative number at 3. I have some negative number at 3. So therefore, we see that my line must touch, not touch, must get as close as possible to my asymptotes but never cross. So it's forced to look like that. Now, what about the middle part? Can you start making a guess of what's going on? So we see we're crossing our x-axis or touching it, and here we have a point below. So we might have an idea of what's going on. Maybe we should pick another point, something to the right of our y-axis. Maybe, I don't know, maybe like 1. Let's see what we're going to do next. For the second piece of the graph, meaning this middle piece right here, we can work with two intercepts. This piece must connect the intercept and further to the right of the curve must continue downward because the curve is only allowed to cross the x-axis at already found x-intercept. On the left side of this piece of the graph, we can evaluate a point to the left of 1. To determine the direction, say negative 1.5. At negative 1.5, we get a positive number. So what it's saying is we have 1 right here. Let's test 1.5 to see what happens. And we see we get a positive number. So we're going to get a point above the x-axis. The piece of the graph must be pointed upward, and the second piece of the graph is as follows. So our graph, we had some point that was positive. So we know that our graph has to get closer and closer and closer to my vertical asymptote. And what I would do here is maybe pick another point, like positive 1. We'll see we get a negative answer. And therefore, our graph must continue touching, not touching, getting close to touching our vertical asymptote, but never crossing. Notice that we have fractions, right? So we're not too worried too much about the value. We're mostly concerned if our answer is positive above the x-axis or negative below our x-axis. The third piece. When we're talking about the third piece, we're talking about this piece right here. The third piece of the graph has characteristics that mirror the first piece. On the left of this piece, the graph must be pointed almost straight upward or downward. This graph, on the right of the graph, must approach the end behavior asymptote at the x-axis. There are no x-intercepts in this region, therefore our piece must be entirely above or below the x-axis, meaning it can either be something like this or something like this, getting close to our asymptotes but never crossing. So let's test a point. Let's test 3 because we have a vertical asymptote at 2. Let's test the number to the right of it. Let's test 3. If we test 3, our answer is positive. We know that this piece of the graph must be above the x-axis. So I have this point above the x-axis at 3. And this point is part of a line that must get closer and closer and closer to my vertical asymptote but never cross, and closer and closer and closer to my horizontal asymptote and never cross. And there we have our completed graph. Therefore, the entire graph can be drawn using a minimum number of points. Now, just to recall, what were our points? We started by finding our vertical asymptote, our vertical asymptotes, our x-intercepts, and our y-intercepts. And from there, I use extra testing points. And the purpose of these extra points is just to see if they're positive or negative. That's our only concern. Example 2. Draw the graph of 3x minus 4 over 2x plus 1. Both the numerator and the denominator are distinct linear terms, so no factoring is necessary. Solving the denominator equal to 0, that yields your vertical asymptote, and you'll get a vertical asymptote of negative 1/2. Since the degrees of the numerator and the denominator are the same, the end behavior, or the horizontal asymptote, will be the graph approaching the horizontal line, negative 3 over 2. I'm sorry, not negative 3, just positive 3 over 2. Again, this is because they're the same degree, so we just take a look at their leading coefficients. The graph below shows the location of all the asymptotes. So we have here our vertical asymptote and our horizontal asymptote. So this splits our graph into 2. I want to see what's going on to the left of our vertical asymptote, and I'm also concerned about what's going on the right of the vertical asymptote. To do this, we must test points. All right, we have extra pieces of our graph we need to figure out. Our x-intercept, our y-intercept, we set x equal to 0, we get negative 4. So I have the point 0, comma, negative 4. For our x-intercept, we go ahead and set the numerator equal to 0, and we get 4 over 3. Here are our x-intercepts and our y-intercepts. Since the end behavior asymptote is a horizontal line 3 over 2, we need to check if the graph touches the end behavior asymptote. So, big note here. We need to check horizontal asymptotes when y equals a number. When it's 0, it tends to work out to where we create a false statement. But when we get an equals some type of number than 0, we need to be careful and check them. Even if they're 0, you have to be careful sometimes. All right, so how do we check our graph? To do this, we must check the function if the function ever reaches a value of the horizontal asymptote. If it is possible that 3x minus 4 over 2x plus 1 equal 3 over 2. So we have to check. We can do so by cross multiplying. So I can multiply 2 times the numerator and our denominator times our numerator. Once we do so, we multiply it out. So we're left with 6x minus 8 and 6x plus 3. Let's move our 6x to the other side, and our 6x's cancel. When adding negative 6x to both sides, we're left with the contradiction that negative 8 equals 3. The equation has no solution. This proves that the graph will never touch the horizontal asymptote. Having one vertical asymptote of the graph will be in 2 pieces. We do not draw each section of the graph one piece at a time. All right, working from the left, the first piece of the fractions graph must have a left end approaching the end behavior asymptote at the x-axis. The right end is approaching the vertical asymptote at x equals negative 1/2, and must be pointed almost straight up or straight down. Because there cannot be any x-intercepts and the graph doesn't touch the end behavior asymptote, we know the first piece of the graph must be above the end behavior asymptote. So we have this graph here. For the second piece of the graph, we can work with 2 intercepts. The piece must connect the intercepts, and further to the right, it must approach the end behavior asymptote. So in other words, we have these 2 points that are part of a line, and this line can get closer to our asymptotes but never cross. So it's forced to look like a curve like that. And there we have our graph. So there is our graph of our function g of x. To shorten the discussion for each problem in this section, we can use the following template to determine all key information needed to graph a rational function. All right, let's do example 3. Draw the graph of q of x equals x squared minus 1 divided by x minus 3. We have a vertical asymptote. We set the denominator equal to 0, which gives x equals 3. The end behavior, or the horizontal asymptote, for this case, we'll have a slant asymptote because we see that the numerator is strictly 1 less than the denominator. I said that backwards. The numerator is 1 larger than the denominator. Since it's 1 larger, since there's a difference of 1 where the numerator is larger, we go ahead and divide. And we can divide using synthetic division for this case because our denominator is linear. So I divide by 3 using synthetic division. We have x squared, no x, so we write a 0 place value, and minus 1. We bring down the first number, and then we follow our rule of multiplying and adding. We do not care for our remainder. We just want our answer. So we get x plus 3. So we'll have a horizontal asymptote at x plus 3. Y equals x plus 3. All right, so we have a y-intercept at 1/3 and an x-intercept at -1. All right, so we have these points. We know these points are part of a figure. Now this figure can get closer to our asymptotes and never cross. So we can assume it's going to look a curve like this. Before I do so, I need to emphasize that your vertical asymptote splits your graph in pieces. So for this graph, we have to consider to what's going on to the right of our vertical asymptote and what's going on to the left of our vertical asymptote. 3. Check if the graph touches the end behavior asymptote. Using the version of the function qx equals x plus 3 plus 8 over x minus 3 and the slant asymptote y equals x plus 3, it is possible that they can touch by setting them equal to one another. Since x plus 3 is on both sides of the equation, it can only be true that 8 over x minus 3 equals 0, something that never is possible since we have the numerator 8 equals 0. We multiply this to both sides so it cancels. In general, if the remainder found during the process of finding the slant asymptote is a number, the slant asymptote will not be touched. The remainder must contain an expression involving the variable to have a chance of touching the slant asymptote. In this case, the graph q of x will never touch the slant asymptote. Draw the graph one piece at a time. The first piece must pass through all 3 intercepts approaching the slant asymptote on the left and the vertical asymptote on the right. Not allowed to cross any asymptote at the piece must be as follows. So we have this part. We know these 3 points are part of our graph that are never going to cross our asymptotes. We drew that one first. Okay, so we sorted out what's going on here, but now what's going on the other side? Well, we can just test a point. Our vertical asymptote is 3. We can test a point like 4. For the second piece of the graph, must be approaching the vertical asymptote on the left and the end behavior on the right. Not allowed to cross any asymptote on the x-axis. The piece must be as follows. And we're forced to have a graph that gets close to our asymptotes but never touches. Therefore, we have this graph here. Example 4. Draw the graph f of x equals 2x plus 6 over x squared minus 9. If we factor our polynomial in the denominator, this factors to be x plus 3, x minus 3. And we see that if once we write it in factored form, we see that we have a value that divides out, that cancels. So our graph can be simplified as this. Vertical asymptote. We have a vertical asymptote at setting our denominator equal to 0, x minus 3 equals 0. We have a vertical asymptote at x equals 3. Now we have this value that canceled out, x plus 3. That will create a hole at x equals -3. In order to find where the hole is located, when x equals -3, we plug in our value into our simplified version. So we plug in our -3 into our simplified version and we get -1/3. So it's a special point at -3 1/3. So we go on as we continue. We go on as our list tells us to. The only difference is now we have added an extra piece. Now we have a hole that we must consider. A hole is just going to be an open circle in our graph. All right, 2 from our list, the end behavior asymptote. The degree of the numerator is 1 less than the degree of the denominator, so our end behavior is y equals 0. X-intercept, we let y equal 0, so it's just our numerator equal to 0. No, I'm sorry, our y-intercept, we let x equal 0. If we let x equal 0, we're left with -2/3, So we have the point 0, comma, negative 2 over 3. X-intercept, we let y be 0, so our numerator equals 0. So we have no y, no x-intercept. So far our graph looks like this. Notice we have a circle with the open that's not filled in. That is our hole that we found. And here we have our y-intercept. So far we know we have a horizontal asymptote that will not cross and a vertical asymptote that we will not cross. And these values, these asymptotes, are drawn as a dashed line because they're not really part of our graph, but we just draw them so we can see them where they are. 5, check if the graph touches your end behavior asymptote, your horizontal asymptote. It's not necessary here since the end behavior asymptote is the x-axis and we have already found that there are no x-intercepts. So we draw the graph one piece at a time. Just to emphasize, our vertical asymptotes split on graph into 2 pieces, and we have to explore each piece separately. Because there are no x-intercepts, the first piece of the graph must be entirely below the x-axis through the y-intercept and containing the hole. So now that we know what it looks like, the reason this is so is because we have these points, and we know these points are going to be part of a line that gets closer to our asymptotes but never crosses, so it's forced to look like that. Now the other side we must explore. So let's test a point that's to the right, say 4. If we test 4, we see it's positive, so it must be above the x-axis. So all I know is it gets close to my asymptotes but never crosses. This is our finished graph. All right, I think we've gone about every single type of example. The extra one is just another example for you to try. I hope you take a moment to look at it and try it out. All the work is provided for you. I'll stop here for the sake of not making the video too long, but if you have any questions, you can always ask me or your SI. Thank you.